Good afternoon, everyone. My name is Brad Scandrett. I am with PowerFilm. We are a solar cell manufacturer. Been around for about 30 years. So we're the oldest solar manufacturer in the United States and probably the only one still making amorphous silicon. So anyway, I'm going to talk to you today about charge controllers, MPPT, and energy harvesting. And why do you need them? So, give you the basics of an energy harvesting system. Many of you may know it, but just for reference. So basically you have some sort of storage element, aka a battery, supercap, that can store the power that's being harvested, some sort of electronics that will manage that power, direct it to the battery, direct it to your power electronics, your load, your device. And then some sort of energy harvesting source. Okay, so TEG, thermoelectric generator, piezo, RF, or solar module. So we'll talk quick about the different sources for energy harvesting. So thermoelectric generators, basically it's the opposite of a thermoelectric cooler. You put heat on one side and cooling on the other side, and with that differential it will generate some power. Papers say you can get up to 0.6 microwatts per centimeter squared per degree Kelvin. So again, you with this kind of device have to make sure you don't reach thermal saturation. So you have to continue to have cooling on the cool side, and you have to continue to have heat on the heat side. It's pretty easy to have a heat source, but sometimes it's hard. Thermoelectric will heat up and the cool side will become as hot as the heat source, and your power, of course, will go down. So piezo, or electrodynamic or kinetic motion vibration type generator, basically takes some sort of mechanical motion and turns that into magnetic energy that generates power. I couldn't really find a microwatts or milliwatts or nanowatts per centimeter squared per frequency of vibration or whatever out there. I can tell you this much: it's very, very low, but wasn't able to really quantify a number on that. So RF, another source, right? Airwaves all around us. More and more RF energy and things being poured into it between AM radio, FM radio, now getting into things like Zigbee and of course Wi-Fi. All these are RF sources that you can potentially pull energy from. Papers say, or some of the data sheets say, up to 1.6 microwatts per centimeter squared, using some sort of antenna and then turning that into power. Solar, photovoltaic, of course, which is I'm most familiar with, basically takes any kind of a light source. Can be the sun, can be LED lights, can be indirect sunlight, and converts that into electricity using the photovoltaic effect. So we produce about 3.2 microwatts per centimeter squared per 100 lux. So at 200 lux you get 6.4, so on and so forth. So your average room is somewhere between 50 and 250 lux. Grocery stores are maybe about 1,000 lux, so you get a lot more power in a grocery store. So any retail operation, you get plenty of power, plenty of light. So elements of an IV curve. So solar modules, for the most part, are very linear in their output until you get down to about 10% of what we call full sun, or 1,000 watts per meter squared of light intensity. Once it drops below that, the series resistance of the panel starts to kind of take over. And with that, the open circuit voltage will actually drop. So the fill factor gets a little softer, the knee gets a little softer, and so if you're in varying light conditions from 200 to 1,000 lux, that's what these graphs show, then you can see that IV curve is going to change where the power point is. On these it goes from about 2.4 volts up to right around 3. And so you need circuitry that can maybe accommodate that. So jumping into it, charge controller, why do I need that? Why do we need something? Well, as you can see from the previous curves and these curves, depending on how many cells you have in series or parallel, the maximum power point of the solar device is all over the place, right? It's series, we double it as far as voltage. If they're in parallel, we're doubling it as far as current, and you need a device that can accommodate that. So with that said, here's another example of not only do you need it for the device, but for the battery. So this shows the graphs of two batteries, say actually the same battery, but being fully discharged and then fully charged. So this is a typical lead acid 12 volt going from 10.5 volts up to 13.5. And the orange graph shows you PWM, a PWM charge controller, which was, I'd say, it used to be the dominant charge controller 20 years ago. And how MPPT will affect that. So when a battery is fully discharged, the PWM will pull the solar panel down to the battery voltage. And by doing so, you basically run on the flat part of the curve, what we call the short circuit element of it. And by doing that, it'll charge the battery at a slower rate than an MPPT. MPPT, of course, will hold the panel at the power point of the max, or excuse me, at the maximum power point on the curve, and convert all of that additional power, which is shown in blue, to current, so charge your battery faster. So on a fully discharged battery, we get about 55% more power, and then even when the battery is fully charged, which is the graph on the right, 13.5 volts, in this case the panel was like a 17 or 18 volt panel, we get about 20% more power. So it will finish the charge faster or energy harvest more during the day by using an MPPT over PWM. So MPPT and data sheets. So it used to be MPPT meant one thing, maximum power point tracking. So the key there, maximum and tracking, right? There are a number of, the MPPT has been loosely used to have different meanings. So there are now, what I saw, fixed PowerPoint tracking, ratio PowerPoint tracking, and then true MPPT. So this graph kind of shows each of those. So the yellow line there would be a fixed PowerPoint tracker. Basically, you set it at a specific voltage. It doesn't really track the solar panel. It will track the battery and still do the conversion and go up and down with the battery as the battery does that, but it will hold the panel at the same voltage. Ratio PowerPoint actually measures the open circuit voltage. You then go in and program the desired ratio depending on the fill factor of the solar module. But as you can see, the fill factor, which is the ratio of VOC over ISC over your VPP over IPP, right? So it's the maximum power point over the endpoint condition. So as that gets softer, the fill factor gets lower, the maximum power point of the panel actually, as you can see in these curves, slides back to the left. So you may be dead nuts on with a ratio PowerPoint tracker when with a cell on a certain thing, and as the illumination of that cell changes based on different lux conditions, you may drift off. Now, it's not a lot of drift. That's what makes ratio PowerPoint trackers pretty good. And the same thing with a fixed PowerPoint. You may drift off of that. It may not matter because you may only be losing a few microwatts, but just a heads up on that end of it. So the different charge controllers. So first, of course, is your PMIC type device, a boost and a buck. So basically, for true MPPT, there's boost topology, which basically takes a higher voltage or lower voltage panel and boosts it up to your battery voltage. The second, buck, which takes a higher voltage solar panel and bucks it down to whatever your battery voltage is. This has been traditionally used in solar. All solar arrays typically will run higher than their battery that they're attached to. Buck topology probably, I want to say, is more than 75% of all the charge controllers out there. But when you get into energy harvesting, it's much more desirable to have a single cell or 2 or 3 cell device because of the small area and the interconnect to put together multiple cells. You typically will have a boost topology that will take a single cell, which may be 0.6 to 1.2 volts, boost that up to a 3 to 5 volt battery. PWM. So again, you have to use essentially a buck type device, right, where my solar panel is higher than my battery voltage. You can do it with a microprocessor. Typically, it can be done without. Why? They're cheap. And there's a lot less parts in a PWM than there is with a microprocessor base. So if cost is important, and you don't need maybe the best performance or the Ferrari-like performance of a circuit, this would be more your average, I want to say Chevy, Dodge, Ford type device. This might work for you great. They are very reliable. In the non-microprocessor, they just run. And I've had PWM type charge controllers in the field for 30 plus years without a single failure. So usually when it's a failure, it's corrosion or something else that takes it out. It's not the device quits working. So both of these, the MPPT and the PWM, work well with all battery types and chemistries. So, and then direct charging, the little dirty secret in the industry. So one of the options may be if, hey, I can't afford a charge controller of any kind, I don't need a huge amount of power, I can oversize my battery and I can use a very small solar panel and I just need to like trickle charge that battery, this may be the option for you. Typically we don't recommend going to more than 1% of the battery capacity, right? So on a 50 amp hour battery, for example, a typical car battery, we say don't run a panel that produces more than 500 milliamp hours. And if you look at that over the course of a day, if you were to put a 500 milliamp hour charger on a lead acid battery and I let it run 24/7, 365 days, yep, it would eventually overcharge that battery. But with solar, we're only on for, I don't know, 3, 5, maybe 8 hours a day, and then it rests through the night. You get a little self-discharge, you get a little backing off of the voltage, and then it starts up the next day. And typically you will never boil the battery in this case. Now, however, this is not at all recommended for lithium batteries, period. Full disclosure, don't use them with lithium. You will overcharge. You can do it with capacitors, works actually quite well. Capacitor doesn't seem to care. If you take it up, it'll just sit there and hold and no current will flow. Becomes, I'm going to say, somewhat resistive. And lead acid. And you can use it with NiCad nickel metal hydride as well, as long as, again, we stick to that 1%. All right, PMIX. Why PMIX? A lot of good reasons for PMIX. So very good at sucking up little teeny tiny bits of power, very good at the circuitry itself being super, super low on the power consumption end. So it doesn't take hardly any power to run these things. You get overvoltage and undervoltage protection, which is really required for any of the lithium battery technologies, and it's good for the other battery technologies as well. You can, of course, do supercaps. You can get primary battery options where if your main system, either the panel or the battery fails, this primary battery, which is a non-rechargeable, can kick in and take over. You can get integrated comparators, and you can get LDOs and things like that, and they're very high efficiency. So PMIX can really cover the gamut on that end for an overall device for energy harvesting. So how do you decide? Good question. And I can't necessarily answer it for you, but I'll try and direct you in the right direction. So this is kind of a quick graph of, depending on your budget, if you need to be really cheap, direct works. Maybe not as cheap, PWM. And then as far as getting into the fixed versus ratio versus maximum power point tracking type circuitries, that's going to get down to how much do you want to spend. Some of the MPPT dedicated chips that are true MPPT can be quite expensive, where the fixed is going to be quite a bit less. So we came out with fixed PPT type charge controllers for a lot of our solar modules a number of years back, because we can build them almost as cheap as a PWM and as reliable as a PWM without a microprocessor, and they actually work quite well. The ratios sit somewhere in between, and we use those for a lot of different applications as well. So how do you get started? So dev kits. Dev kits is a great way to get started. It'll get you basically everything in my really first full slide: the battery, the electronics, and some energy harvesting devices. Everything from EPs, ST Micro Maxim, Analog Devices, TI, Nordic, they all make some sort of energy harvester that you can take a look at. All right, so we'll jump into the energy harvester IC comparison chart here, and I just kind of threw this together to give you kind of some bullets as to why you may want to pick one or the other. If you want to pick the most expensive chip and you need to use vibration for energy harvesting, the Zytus EHM UNIV-1 will be the chip for you. It actually does very good on quiescent current, and it's got a nice LDO regulator into it with decent output. It is a large chip, 25 millimeters by 25 millimeters, and it's 45 bucks a piece. So they are crazy expensive, but they're the only ones that do vibration. Beyond that, if you need the most or the least amount of power consumption and the best, I want to say, at grabbing little bits of power, the EP's AEM 10941 will suck up 3 microwatts of power on the low end, and it's got a very low quiescent current, second only to the Zydus chip at 400 nanoamps. It's also fairly reasonable at $3.87, and this is a 100-piece quantity. ST Micro has a very high current device, not I would call a true energy harvester, but if you got an application where you're going to be outside in the sun and hey, I'm going to have plenty of power available and I want to be able to maybe take advantage of that, this thing will go up to 1.8 amps. It's also the cheapest chip at $3.28 in a 100-piece quantity. TI makes a number of BQ chips that are quite good, have a very good input voltage range from 0.1 up to 5.1 volts, narrowing out the EPs by 0.1 volts on the top end. Analog devices, they will also do, they're the other one next to EPs that will have a primary battery option. And if you need a really, really small chip, Analog Devices Maxion 2361 comes in at a 1.23 by 1.63 millimeter package. I couldn't get costing at 100K, or excuse me, at 100 pieces on that, so you get 1K pricing at $3.30, but I would guess it's in that less than $4 range. So 2 of the devices I showed, which was the Nordic and the TI CC2650, those are Bluetooth coupled with energy harvesting BQ chips, a BQ 25570 energy harvester, and we packaged those together so you could do a little bit of low energy Bluetooth transceiver information. So if you needed to transmit information over the Bluetooth network, you can do that. The Nordic Semi chip also offers Bluetooth mesh where you can communicate, hop from one to the next. So if you need to set up a mesh network, that's a fairly easy way to do that in the Nordic's NRF52832. So if there's any questions at this time, I would be happy to address those as time permits. If we go beyond that, you can go check us out on our website, get a hold of us. We'd be happy to answer any of those questions. And again, thank you for your time.